All right, so this is one of the problems that was on the first exam, and we saw that some students had some challenges with it. Let's go ahead and go about solving it now. So first we see that player kicks a ball, so that ball would be in projectile motion, and we know the point in which it hits the heel. So that gives us enough information to determine the speed at which it was kicked, as well as the speed at which it hits the ground. So let's go ahead and get started working. Switch to my camera here. So the first thing we're going to do is to set up our coordinate system. So we're going to say that our origin is here, right? X and Y coordinates, right? And we know that the ball is kicked, and it gives us, the problem tells us, the angle at which it kicks. So it was kicked at VA, that's the velocity at point A, and we know that it was kicked at an angle of 30 degrees. What we also know is the point at which it strikes the ground. Now, the actual curvature of this, which is given by this equation, y equals negative 0.04 x2, does not mean anything. That is only relevant in the event that the projectile actually travels along that path. So what we really need is the distances that were given to us. And so we know that at this point B, when it strikes the ground, that is the distance of 15 meters in X, and it is a negative 9 meters in the Y direction. Okay? So when we're talking about projectile motion, what we have is we have an initial direction without a magnitude, and we have initial position and a final position, and that gives us enough to begin to solve this problem. So the first thing we'll do is set up our equations of motion. So in the X direction, we'll start with X is equal to X naught plus V naught in the X direction times T. Okay? And in the Y direction, we'll have a similar equation, which is Y is equal to Y naught plus V naught in the Y direction times T minus 1/2 GT squared. Now, in the original equation, you'll see it's 1/2 AT squared, but we know the gravity of a projectile is always negative with the magnitude of G, which in this case we're using meters, so it's 9.81 meters per second squared. So those are our two equation of motions that we can work with. Well, we know initially, because of where we establish our origin, that y0 and x0 are both 0. So x0 and y0 are both 0. And because we know that the ball hits at point B, then this x that we're trying to determine becomes xb and yb. So once we know those values, we can plug this in and begin to solve. So we see that xb is 15. So 15 equals v naught in the x direction times t. And then negative 9 is equal to v naught in the y direction times t minus 1/2 gt squared. Okay? And so now we have our classical two equations with two unknowns. Well, it looks like it's three unknowns because our unknowns at this point are v naught x, v naught y, and t. But we realize that there's a relationship between v naught x and v naught y that's given by the angle of 30 degrees. So what we can say is that that relationship says that VA cosine 30 degrees is Vx. I'm writing it kind of backwards, but and VA sine 30 degrees is Vy, right? Or V naught y. So we can substitute that in so that this can be an equation, two equations in terms of VA and T. So if we do that, we'll have 15 equals VA cosine 30 degrees T, and negative 9 equals VA. And we know that the cosine of 30 is 1/2, so we'll just go ahead and move that to VA over 2 times T minus 1/2 GT squared. All right, you guys still with me? All right, so from this point, we have two equations with two unknowns. And so we solve that by substitution. And so the first step we can make is that we can actually solve for T, right? So if we solve for T, we can substitute that in. So we know that T is equal to 15 over VA cosine 30, and that's directly from this equation here. And then we substitute that T into the second equation. So let's do that. So -9 is equal to VA over 2, and then our T in this instance is 15 over VA cosine 30, you know that's 30. And similarly for the other term, 1/2 G, and it's T squared, so that would be so that would be 15 over VA cosine 30 degrees squared. Okay? And so if we continue solving this, we can realize that one, in this instance, VA over VA, this cancels out. So we have that, and we end up with an equation with VA squared on the bottom. So to skip through the math, essentially as you solve this, you would end up realizing that VA squared would be equal to a quantity 4330 over 17.66. So you take the square root of VA, the square root of both sides, so here and here. So VA, yes, we're still there, would be equal to 16.5 feet per second. Okay? Actually, no. We're in that would be, excuse me, that would be meters per second, right? Because we're in meters. So that would be our first step. We establish what VA is. And by going through this method, we get VA, and we don't have to start with VA of X and Y and decompose. So once we've done that, there are actually two ways to go about solving for the velocity at point B. I'll do the most classical method, which is to continue solving here because we had two equations with two unknowns. So let's go ahead and solve for T. And so if we solve for T, we go back to this equation here. So T is 15 over VA cosine 30 degrees, and that gives us that T is equal to 1.047 seconds. The reason why that's important is because we need that for our second equation. Actually, let me figure out. Okay, so see if we can squeeze this in real quick. So with respect to the velocity in the x direction, since there's no acceleration there, it's constant. So we know that VBX is equal to VOX, right? And so that's equal to VA cosine 30 degrees, all right? So we know what VA is now, and so we can easily solve for what VBX is. Now VBY is due to constant acceleration, so we have VOY, the initial velocity in Y, plus AT, which in this case would be minus GT, okay? And the good thing is we know what T is, we know what V naught of Y, so we can just solve this algebraically. Once we've determined what VBX and VBY are, then VB, because this is a vector, would be the quantity of VB would be the square root of VBX squared plus VBY squared. So that would be the magnitude of VB. And then, just for completeness, the vector VB would be the actual quantity of VBX in the I direction plus VBY in the J direction. So that would be the vector and the magnitude of the velocity at impact at point B. And that's the solution for the second problem in our first exam.